Poolside released Laguna S 2.1 on July 21st, and the headline is wild: a 118 billion parameter agentic coding model that the company says is compact enough for serious work on local hardware. The specification reads like 3 different models collided: 118 billion total parameters, roughly 8 billion active for each token, and a context window reaching exactly 1,048,576 tokens. But local does not automatically mean laptop-friendly. The full BF16 checkpoint needs multiple GPUs and roughly 236 gigabytes just for weights, before the rest of inference joins the memory party. The key is mixture of experts. Instead of pushing every parameter through every token, a router selects a small subset of specialized expert blocks, reducing active computation while the whole model remains stored. Laguna S 2.1 contains 256 routed experts plus 1 shared expert. For each token, its token choice router activates the top 10 routed experts rather than waking the entire collection. That explains the 8B active label, but not away the memory requirement. Active parameters describe work per token. Total parameters still matter when the complete 118B model must reside somewhere accessible. Its 48-layer stack mixes 12 global attention layers with 36 sliding window layers, a 1:3 ratio designed to preserve occasional broad awareness without making every layer inspect the entire context. A sliding window layer looks across a 512 token neighborhood. Visually, imagine a narrow spotlight moving along a huge sequence, processing nearby relationships without repeatedly scanning every token behind it. Global layers provide the counterweight by connecting across the broader sequence. The architecture alternates these wider checkpoints with cheaper local windows, rather than choosing only one attention pattern for every layer. The maximum context is not shorthand marketing. The model card specifies 1,048,576 tokens. Laguna supports native interleaved reasoning. It can reason, call a tool, inspect the result, and reason again, instead of confining all deliberation to one block before an agent begins acting. Poolside recommends preserving earlier reasoning blocks in message history. If an agent drops them while reconstructing later turns, the model may stop generating reasoning during follow-up steps and lose that continuity. At launch, S 2.1 offers only thinking off or max, with max enabled by default. There is no low, medium, or high effort dial yet, so control is blunt. According to Poolside, max thinking lifts terminal bench 2.1 from 60.4 to 70.2%, while Deep's WE jumps from 16.5 to 40.4%. That is a substantial measured difference. The cost is trajectory length. Poolside reports mean thinking mode completions of 129,000 tokens on terminal bench and 249,000 on Deep SUE, with some coherent sessions lasting several hours and hundreds of thousands of tokens. Now the skeptical part. These are Poolside published comparisons. Its tables combine vendor self-reports, benchmark leaderboards, and third-party figures, so every number needs methodology attached, not just a victory animation. Poolside reports 70.2% on terminal bench 2.1 in its agent harness with thinking enabled. That benchmark connects an agent to a terminal for a broad set of long horizon tasks. In Poolside's July 21st table, S 2.1 lands near 10-cent high 3 at 71.3, despite Laguna listing 118B total parameters against high 3's 295B. Efficient does not mean dominant, but it is notable. Deep SWE is the sharper warning label. Laguna scored 40.4 in Poolside's pool harness, while the official leaderboard uses mini SWE agent. Poolside explicitly says those harness differences make scores less comparable. A genuinely useful move. Poolside published final evaluation trajectories for inspection. Its archive says terminal bench results use pass at 1 over 4 attempts, though timed out attempts may not produce a trajectory. In one Poolside case study, Laguna spent 50 minutes and 181 steps building an HTML and CSS rendering engine from an empty folder, then compared its canvas output numerically against headless Chromium. Poolside also reports that an automated Laguna loop made its agent harness 5.2% faster while cutting memory allocation by about 70%, with race detection and vet checks enabled. The strangest case is mathematics. Poolside says Laguna independently rediscovered a proof family for Erdos problem 397 during a 68-minute offline session, using Perl after discovering Python was unavailable. Poolside's own explanation is behavioral, not magical. More verification, less premature victory, greater persistence, and willingness to backtrack. The company argues this working style is a separate axis from raw intelligence. S2.1 used the same pre-training data as XS 2.1. Poolside says most separation came afterward, supervised fine-tuning to bootstrap capabilities, followed by reinforcement learning on tasks the model rarely solved. Poolside describes 409,000 post-training environments, including 83,000 terminal setups and 168,000 software engineering workflows. Many software tasks reconstruct real commits, merged pull requests, injected bugs, or deleted files. The training loop received longer timeouts, more tokens and turns per task, improved sandboxes, and multi-harness rollouts. Poolside thinks those larger budgets are one reason the model learned persistence. For deployment, Poolside released BF16, FP8, NVFP4, and INT4 weights, plus official GGUF and MLX conversions. That gives builders several ways to trade precision and compatibility against memory pressure. Quantization reduces the footprint substantially, but it does not turn the full model into the 8B model its active count might suggest. The checkpoint still represents 118 billion total parameters. Official GGUF conversions target llama.cpp style local serving, but Poolside currently directs S2.1 users to its Laguna branch for full support, including dflash, while base support remains under upstream review. dflash adds speculative decoding. A smaller trained draft proposes tokens ahead, and the main model verifies them. Poolside's VLLM recipe allows up to 7 speculative tokens to lower serving latency. The official routes include VLLM, SGLang, llama, transformers, TensorRT LLM, and llama.cpp, alongside hosted access through OpenRouter, BASE10, and Vercel. Local and hosted are both first-class deployment choices. Poolside says S2.1 can run on a single NVIDIA DGX Spark. That supports the local claim, but also clarifies its scale. This is workstation class local, not casual background inference. For ordinary local builders, Laguna XS 2.1 may be the more practical story. It launched separately on July 2nd, 19 days before S2.1, so it is a companion, not part of the new release. XS 2.1 has 33B total parameters, 3B active per token, and a 262,144 token context. Poolside describes it as compact enough to run on a Mac with 36 gigabytes of RAM. Poolside also released dflash speculators for XS checkpoints and reported roughly double the achieved tokens per second in its tests. Useful, yes, but remember that is a vendor-measured performance claim. Poolside openly lists harness overfitting and nested tool call failures. Slight schema changes can trigger an invalid first call, while JSON array arguments may emerge incorrectly, escaped until the harness rejects and retries. So yes, 118B frontier-style coding can now live locally, but on serious hardware, with quantization choices and benchmark caveats attached. For many builders, the 33B sibling is the smarter place to start.